I've had several people ask for help on worksheet number 2. I'm going to leave 1 and 2 to you. We talked about those. If you do have individual questions, feel free to send me an email or log on during one of the Zoom meetings. I'll have one on Monday at 4. The worksheet's not due till midnight that day, so you can still ask questions then. Let's take a look at this last one. Now, I've added a section of a chromosome for this one, so your worksheet doesn't have that. But given a large section of a genome, say you have a complete chromosome, how would you locate genes? Now, a chromosome is just hundreds of millions of molecules, these base pairs sequenced one right after the other. And so A's, T's, C's, and G's, and there are no spaces or periods or paragraphs like you'd have in an instruction manual. It's all just one long string. But the genes are in there. We're going to talk more about how much of your genome is made up of genes and a little bit about arrangement. But for now, just know it's like kind of like looking for a needle in a haystack. Now, the most common answer that I get, this is an incorrect answer, but I just want to get it out of the way because it's a common misconception, is people say, oh, if I want to find a gene, all I need to do is look for start codons, okay? So I'm going to zoom in here a little bit so you can see the A's, T's, C's, and G's a little bit. And this is one I just cut and paste from GenBank, which is a government-sponsored repository for DNA data. Okay, so I'm going to look for find and say ATG, that's a start codon. Now look at this. We have 17 ATs and Gs in this sequence. So are there 17 genes here? And the answer is no, there aren't 17 genes. So why are there so many ATGs? Well, think about this. In non-coding DNA, AT and G can still go together. There's no rule against that. They don't have to be a start codon. Number 2, methionine, AT and G codes for methionine. And although methionine is the first codon in genes, it's also a perfectly valid amino acid in the middle of a gene. So this could be non-coding DNA. This AT and G could be a methionine in the middle of a gene, not a start gene. And not only that, but this ATG, even if it's inside of a gene, might not represent a methionine. The A and T may be part of the codon before, and the G may be the part of the next codon, or so on. We don't have any indication of reading frame. Okay? So, how can we then go about finding genes? Now, another common thing I just want you to be aware of, I think someone put this on Homework Hero or Course Hero or anyway, one of those worksheet sites, and it's really wrong, but I think it's the most common one. I get this all the time from people, and it's dead wrong, so be careful, don't put this. I get all the time that people say, you would use sequence inspection because a gene is not just a random string of base pairs. And so anyway, saying that is a little bit like if I asked you how to drive a car and you said you would use vehicle translocation, which technically is correct, but is so vague it's completely useless. So don't put sequence inspection, please. Okay, now there are 3 ways that we can do this, so let's list them here. The first is called, we can look for an open reading frame. Sometimes this is abbreviated ORF. Now, what this means is we don't look for start codons, we don't look for stop codons, but what we do is we translate all 6 possible reading frames, and then we look for a long stretch that is lacking a lack of stop codons. On average, about 1 out of every 17 or so codons in any random reading frame is going to be a stop codon. So if we have a long stretch that's 100 codons long with no stop codons, that's a really good indication that that's a gene. Okay, so that's one thing that we can do. Another thing that we can do is we can identify promoters. Now, I just randomly cut this out of a piece of chromosome, and the way that chromosomes are arranged, it's very, very unlikely that there's a gene in here. But we could, and you could probably do this. In fact, let's just see if we can do it very quick. What is the eukaryotic promoter sequence? And this is fairly well conserved, and all genes have a promoter sequence somewhere in front of them. Sorry, eukaryotic promoter sequence. And there are a couple of them. There's some variety and diversity in this, but many of them are very, very similar. So I've got a list here. The Tata box is the most common. There are a couple others. So the consensus sequence, this is not great because even though it's more than 3 base pairs, here we go. There we go. So this one, so the promoter sequence has 2 of them together. This one's a little bit longer. It's going to highlight it, but it won't let me do that. It would be nice if that was text, but I guess it's just an image. So we'll put them both on the screen and say, hey, let's find a promoter sequence. Okay, so upstream of the gene, 32 base pairs is going to be TCTC. N means it could be any of the above, so Word has trouble differentiating that. So an N in a sequence means it can be a C, it can be a G, it can be a T, it can be an A. So just for simplicity's sake, I'm only going to search for the end of this one, CCC, TT, GAA. And there are no matches. So that is a much less likely to have just by random chance. What is that? 9 different base pairs in a row. If we add on those 4, then in essence we have, those 4, we have like 13 base pairs in a row. So we can look for promoters. Okay, so back to this. The third way, which is actually the most complete and exhaustive way to do it, is map a transcriptome onto your genome. Now, I'm not going to get in a lot of detail here. A transcriptome is basically when you sequence the mRNAs that are being used. So any gene that is being used will be present in that transcriptome. So if you have this long sequence, you can then map it back onto a genome or a chromosome and find any genes that were expressed in that transcriptome. Okay, so those are the 3 different ways. C is the most exhaustive and effective way to find genes. Now, for a large section of a gene, so if you knew you were in the coding region, all you would have to do is look for open reading frame. Okay, so one of the 6 reading frames will have no stop codons, all the rest will have stop codons just because they pop up about every 17 codons by chance if it's not the correct reading frame. So open reading frame is the best way to do that. Now, this last one's a little trickier. I've got different sequences here that are in your worksheet. So this will show you exactly how to do it, but don't copy the answers exactly because you just have to learn how to do it using my example and then use it for the sequences that have been provided on your worksheet. Okay? So you could, if you wanted to, do open reading frame. Do all 6 possible reading frames. You need to do the 3 possible forward reading frames, the reversed 3 possible reverse reading frames, but number 1, these have been given to you in the correct orientation, so we only need to do the forward reading frames. But even that's a lot of work. I don't expect you to look at all 3 reading frames for armadillo, all 3 reading frames for the horse, and do that. You could, but that would take you forever. Now, if you did that, it might not even work because it's such a short sequence that just by chance, some of the non-coding reading frames might also be lacking in stop codons also. So that works over long stretches where it's just pretty much impossible for you not to have a stop codon in the non-reading frames. But for short sequences, it doesn't work. So there's got to be a better way. And this is tricky, but it puts together a lot of the topics we've been talking about. So I want to walk you through it, and then I'll just kind of give you the easy take-home way to do it. But I want you to understand why this works. So first off, we need to think about mutation, right? So I've asked, first, I thought I'd ask you to think about, the nature of evolution. So let's break it down. So first, mutations. Now, mutations are effectively random. So if mutations were the only thing going in here, we would expect to see diversity as new mutations brought in diversity, but no clear pattern. Okay. Now notice we have mutations. Everywhere there is a difference in one of the species, that represents at least 1 mutation. And in some cases we might have 2 different mutations, where here we have the killer whale that has a guanine at that position and the cheetah has a cytosine. But at least 1, maybe 2 mutations have occurred at several of these sites. But then there are a lot of sites that are conserved. There are no mutations at all. Okay. So mutations give you the diversity, but no clear pattern upon which we can decide what the reading frame is. So we need to add in natural selection. Now, when a mutation happens that is neutral, there is no natural selection. So natural selection will not be acting if it's a neutral mutation. And so if we look at the genetic code, where do most of the neutral mutations occur in reference to the reading frame? And the short answer is at the third position. You can change the third position in many, many instances. In fact, about 85–90% of all possible changes at the third position result in a neutral mutation. So natural selection wouldn't do anything to those because by definition they're neutral. They're not going to be good, they're not going to be bad, and so there'll be no force either keeping them or removing them from the population. So we'd expect to see a number of mutations at the third position. But what about at the second position? Now, by definition, they're not going to be neutral because they're going to always change the amino acid. So notice CCC is proline, but if I make it a CAC, it's histidine, or a CGC, it's arginine, or a CTC, it's leucine. So that's always, you can look at the examples and convince yourself of that, or just take my word for it. Changes at the second position always will make a difference in the amino acid. And so if it's not neutral, which if we change the amino acid, by definition, at least at the protein level, that's not going to be an insignificant change. What is the outcome? So remember the pie chart. The very first pie chart I showed you in the lectures was mutations, just mutations, right? But remember, of the vast majority of those mutations are going to be neutral. We're not looking at those right now, so we're looking at that less than 5% that remains. And of that less than 5%, the vast majority of those are negative. And so those are going to be removed by natural selection. So mutations at the second position are almost always going to be removed by natural selection. So when we come along millions of years later and sequence this gene for the armadillo, horse, killer whale, cheetah, and chimpanzee, we're not going to see all of those mutations, even though they've been happening because they are random, but we're not going to see them at the second position. We'll only see the ones at the third position because those are neutral. And so in the vast majority, we'll talk about a few exceptions to this rule in a later chapter, but in the vast majority of genes, because they have a very important conserved function, we can see this pattern where we will have, and now notice it here, we'll look at it fairly clearly. No mutations in the first column, mutation. No mutation, no mutation. There's a mutation. No mutation, no mutation, mutation. Now here we don't see it because same, but now notice same, mutation. Same, mutation. Same, mutation. So you have to look for that pattern. Not 100%, but maybe 90–95% of all mutations are going to be at the third position in the reading frame. So now that we know that, we have established the reading frame and we can move on for the rest of it. And so for this one, again, it's randomly cut out. I don't remember. It may be different for the one you've got, but look for the pattern. And so here, second position, third position. First, second, third, and I've established the reading frame. Once you've established it, it's going to be the same forward and backwards, no spaces. That's the nice thing about the genetic code. So I can't translate this codon because it's only a partial codon. So the first complete codon doesn't start until that C right there. And so I would go CGG, come down here and say CGG. That's an arginine abbreviated with an R. And I'm going to put an R here for the armadillo. Now, I could go ahead now and do the next one, CGG, and then GGC for the armadillo. And I could keep going and translate the first amino acids, then move on to the horse. That's a little bit more time-consuming than this way. Instead of moving on to the next codon for the armadillo, let's look at the codon below for the horse. Same position, CGA. CGA. Yep, sure enough, that second position changed, but it's still an arginine. And in fact, if we look at all of these for position 1, they're all going to be arginines, either CGG or CGA. The next one, GGC. GGC is a glycine abbreviated with a G. I put that there. Now notice they're all GGA after that. So GGA, yep, sure enough, it was a neutral mutation. It's kept around, was not removed by natural selection. That's why the diversity is there at the third position. And then I would go on and I would translate the rest of these. Okay, so do that. And what you should see is that we have very little difference or divergence. I can't type, sorry. Very little divergence at the amino acid level, despite some differences. And if you want, you can think of those as mutations at the DNA level. So your amino acid is much less divergent than your DNA, and that's always the case. And so the reason is because nucleotide changes at which codon position most often lead to synonymous or silent mutations. It's that third position in the reading frame. Okay? And then the only other thing, hopefully you got this, but I also asked, how do you know? So the first complete codon in this one, again, it might be different from yours, so double check. But in this one, the first complete codon begins at the third column in the alignment, or you can say third position in the alignment. And how do we know? We know because of the pattern of mutations. All right, hopefully that helps with worksheet number 2. If you have any other questions, feel free to send me an email or check in at the Zoom meeting Monday at 4 p.m.